have my good friend Kevin Zumbrum back here. He has been a friend for about 10 years or something like that. And we initially worked together on the internal structure of shock fronts. And then we found all sorts of strange possibilities. And he went on his own to understand whether those possibilities were physically reasonable, in other way, stable, in other sense, or not. And he came up with methods that actually are much more powerful than that. They can actually be extended to whole shock fronts in more than one spatial dimension. That's what he's going to tell us about.
Okay, first, let me thank the organizers for the opportunity to speak on the occasion of this 50th birthday celebration, and to add my best wishes to IMPA for the future. Dan gave a good introduction to my talk. I'm speaking on a general program. It's not. It's a series of results with many collaborators. I'll try to mention them as I go. And in brief, we're trying to recapture the program of Andy Maida carried out in the hyperbolic setting. That would be a short way to say it, and extend that to the setting when viscosity is included in the equations. I'll say more. So the starting point is in the hyperbolic setting. So let's look at a set of hyperbolic conservation laws in multi-dimensions. This consists of a vector U of conserved quantities, physical quantities, flux, and a first-order homogeneous equation, spatial dimension D. And there are many examples that fit this abstract framework, and just perhaps the Euler equations for gas dynamics should be the example to keep in mind here. But there are many others: elasticity, magnetohydrodynamics, and phase transitional flows also fit this. And the fundamental feature from the point of view of this talk, this goes back to observations of Riemann, is that these equations support shock waves, traveling discontinuities. And here these have a planar structure. So U of xt is given a solution U bar of x1 minus st. x1 is the first component only, the normal direction to the shock. And if, so it has a one state U minus to the left of the front, and one state U plus to the right, and there's a sharp discontinuity at x1 equals st. Okay, now there's another point here. Not just any discontinuities are physically admissible. We must satisfy the equations in a weak sense. That is, we must have conservation. And this means we have to satisfy Rankine-Hugoniot conditions. And here they're just written down for you. The brackets mean jump in the quantities across the shock. So these are the standard Rankine-Hugoniot conditions. And we could view this as, I lost the sign there, we could view this as a generalized dispersion relation, a nonlinear dispersion relation. It gives the speed implicitly in terms of the jump of the wave. And this was formalized in this form by Hugoniot already in 1887. Now, a couple remarks. The first one looks strange. Say the waves predate the equations. Not only in the obvious physical sense, but also mathematically. That is, people first looked at the flow problem from the point of view of this dispersion relation and waveforms, superposition of waveforms. For example, Poisson looked in this way, Challis, Stokes, and I think Stokes was the one who observed discontinuities must form, and then this leads on finally to the equations. But okay, so anyway, also the waves are really there. You can observe them at least on the correct scale. So this is a successful model already. This very successful model. The hyperbolic conservation laws. Also, there's a well-developed theory now of existence and stability of shock fronts, even curved shock fronts, not only the planar ones I displayed there. And this goes back to there are important contributions in each decade, starting from the 60s. Erpenbeck, Kondratyev, Diakov studied just the linearized stability problem. That is sort of a normal modes analysis. And this was fundamental because up to then, I think maybe the person who began studying this was Kondratyev. Before that, people thought shocks were just stable. They couldn't be unstable. So he did the algebra, found out that they could be unstable in some situations, and that was quite dramatic. I think Erpenbeck was the first to get all the details right. And then I mentioned Agman, Kreis, and Sakamoto. They worked on boundary value problems. It's related, not quite the same, but introduced some, Agman did a direct analysis. Kreis and Sakamoto independently came up with methods for treating nonlinear problems. That is, they did the linearized analysis in such a robust way that it could be extended by pseudo-differential techniques to the nonlinear problems. And Maida used those techniques very heavily, but this is probably the most fundamental contribution here in terms of mathematical foundations. This made it mathematically rigorous, and this was in the 80s, so Maida showed the existence of curved shock fronts for hyperbolic conservation laws, and that involves proving stability, because you have to construct these through an iteration scheme. Then there's some really fundamental contributions also of Metivier in the 90s, and he studies the weak shock limit, that is, the limit in which the end states approach each other, so it looks like a constant solution. Now, sort of counterintuitively, that's a very singular limit for this shock stability problem, because it's sonic, it's non-characteristic, and somehow the stability, many of the estimates, much of the stability comes from the fact that signals are entering the waves transversely. Okay, but we'll come back to that. And I mentioned that the general Cauchy problem that for rough data is unresolved in multi-D, and it's not clear that it's resolvable because for various reasons. But nonetheless, around these special solutions, we can do a complete theory, the Maida theory. And I mentioned also, in some less standard settings, even magnetohydrodynamics, certainly in phase transition and detonation, there are some philosophical difficulties, even how to set up the problems. And that has to do with the fact that sometimes, in some settings, the Rankine-Hugoniot conditions alone are not enough to determine the physical waves. They have to be supplemented carefully with other conditions. Then it's not clear how to set up the stability problem. Okay, so that's the background to keep in mind. Now let's go to the viscous setting. So by a viscous conservation law, I just mean the first order homogeneous hyperbolic conservation law augmented with some second order terms. And these are semi-parabolic. That is, the matrix here, Bjk, it satisfies a semi-definite parabolicity condition. So this is the case for physical examples, Navier-Stokes, magnetohydrodynamics, et cetera. That's because there's no diffusion in the mass equations, basically. Also in some, basically in the Maxwell equations either. Okay, so the first question is, what happens when we incorporate these finer scale effects? It turns out that under a dissipativity condition identified by Kawashima, these equations support viscous shock profiles. Now, these are smooth traveling wave solutions which interpolate between U plus and minus. They give an inner structure to the shock wave, but they are smooth. So they have limits. Their limits at infinity are the end states for the jump discontinuity for the associated hyperbolic shock. And this occurs whenever the triple U minus U plus S satisfies Rankine-Hugoniot condition. This problem you might call the planar vanishing viscosity problem, because we're trying to approximate planar hyperbolic shocks as a limit of smooth parabolic traveling waves. And this goes back, Stokes, Gelfand, Gilbert, Conley, Smoller, Maida-Pago, and Pago all have big contributions to this problem in different ways. The dissipativity condition, by the way, is very natural. It's a coupling condition. It basically says that the hyperbolic part of the equation, the parts with no dissipation, must be coupled in a certain sense to the parts that do have diffusion. And that's natural because otherwise there could be a completely decoupled equation, and the hyperbolic part might support shock waves that were not smooth. So it's clear something like that must be necessary, and that's really enough. So that's a very interesting contribution. And by the way, that condition is satisfied for all the physical examples I mentioned. So that more or less covers the viscous planar existence theory. Now, some remarks here. When we put these effects in, then the Cauchy problem here, now it becomes approachable. And although I wouldn't say it's complete, and I mentioned some work by David Hoff, Pierre-Louis Lyons, and many others recently. But now the existence and stability for systems of multidimensional curved shock fronts, that was completely open until the initiation of these projects. Okay, we'll see why a bit later. But basically, it's the same problem as in the hyperbolic setting. We have planar fronts just sitting around. We can solve an ODE. But the curved ones essentially have to be constructed in some way. We don't have simple examples. So, and I mentioned that even the one-dimensional stability, a complete stability result was first obtained only in 1992 by Sepeschi and Shin. So, and that was by very different methods, but that's not very long ago. So the viscous theory has really lagged behind the hyperbolic theory until now. And the questions we're addressing here are the viscous models accurate? So viewing these the shock waves themselves as the fundamental aspect, do these equations give stable, smooth shock fronts, planar and curved? In particular, can we recover the Maida and the Metivier theory? And what is the precise relation to the old hyperbolic theory? And a second one, maybe this is the biggest motivation for studying, can we get more information from the viscous models? And in particular, are these transport effects, these diffusive effects, going to fix the point of transition to instability? And that is undetermined, by the way, in the hyperbolic theory. That's an important point. I'll come back to that. And for these non-classical cases where there are philosophical difficulties for the hyperbolic theory, can we now address those? Can we fill in those gaps with these extra, taking into account these extra effects? And what about more general setting, kinetic models or relaxation? So the starting point here, as in the hyperbolic theory, is planar stability. Of course, we have to start somewhere. So first of all, let's look at the hyperbolic stability. Now here, I've written some analysis, but most of it's not, the details are not so important. Basically, we do a linear interface analysis. It's a very standard one in the same way as general hydrodynamic instability studies. So we look at we linearize around the ideal shock. This is the jump discontinuity, and that gives us constant coefficient equations for positive x and negative x1, and they're linked by a linearized jump condition, linearization of Rankine-Hugoniot. So it's a transmission problem with constant coefficients. And we look for normal modes. That is, we look for solutions of these linearized equations, which are Laplace Fourier transforms. So they vary in x1, and they have exponential sinusoidal behavior in t and x tilde being all the transverse variables, x2 through d. But when we do this, we have left, that leads to an ODE in x1. So we can look for, and these are basically generalized eigenfunctions if they exist. We must ask that they be decaying, and we have the jump conditions as well. This turns out to be enough to close the ODE, give a closed system of ODE, and we can solve. What we get is an algebraic condition. That's because, why? That's because our ODE is constant coefficient, because it came from the ideal shock situation, which is constant to left and right. Therefore, we can explicitly solve the ODE to the left and right of the boundary, and all that's left is an algebraic system involving the jump condition. So therefore, we get a determinant condition. We take a certain determinant, which I'll call delta. It depends only on the frequencies, the Fourier transform frequency, c tilde, in all the transverse directions, and the Laplace transform variable lambda in time. This determinant, which depends on those, must be 0. And here I've written it out. It's not, for those of you who know it, but it's not so important, the details for this talk. Basically, its columns are eigenvectors of a certain matrix that comes from the coefficient matrices of the problem. So A, J are involved. These are the Jacobians of the flux functions, and that's it. Stability requires that this not vanish for real part of lambda greater than 0. Why? Because vanishing of this determinant, recall, meant solvability of the eigensystem, and that meant the existence of an eigenfunction for those frequencies. If I have growing modes, it's clearly unstable. Now, let's go just make a couple simple remarks about this. This is the main point of this slide. First of all, this function delta, this determinant, is homogeneous degree 1. That's all. It's not linear. It's homogeneous. And so it has conical solutions. So the spectrum is conical. If I have stable modes, they go along rays. So everything's scale invariant. If I have unstable modes, I have instability in a very strong sense. It's Hadamard instability. The problem is ill-posed. And an interesting intermediate case is neutral stability. It's called what might have called weak stability. That's when you have spectra along the imaginary axis. And this corresponds to, with everything else, negative in real part. And this corresponds to a surface wave. So if you have a frequency lambda equals I tau, tau real, that corresponds to a surface wave, a traveling wave solution that moves along the front with speed sigma given by tau over the transverse frequency, C tilde. And this is Midas' big theorem, the strong spectral stability condition, that is this left case, no surface waves, implies nonlinear, not only linear stability with strong estimates, but nonlinear stability. And the neutral case, we don't know. And that's the reason that that instability is not determined by the hyperbolic theory. Basically, it turns out there's a gap. As you start with a small amplitude wave, you start in this strongly stable regime, generally, and then there's a band of shock strength for which it becomes weakly stable and supports surface waves. And then after that, it becomes strongly unstable. Somewhere in the neutral stability regime is where the transition to true instability occurs, and that requires more information. Okay, let me mention some, I have a picture of that below. Let me mention some applications of this theory. Very successful application to gas dynamics, because here, this determinant is explicitly evaluable. This was done by Erpenbeck, and it can be related to the geometry of Hugonio curves. The Hugonio curve is the curve, if I fix at one end state U minus, I look at the curve of all other states U plus that can be connected to it by the ranking Hugonio conditions. That's the Hugonio curve. And it turns out, by the way, shocks are just stable for ideal gas dynamics, for any amplitude. I mentioned in phase transitional models, with suitable modification, one can obtain useful results. And Freistüller did this in an abstract setting. Sylvie Binsoni, Gavage actually carried it out in some cases. But you don't get all information. In magnetohydrodynamics, I think it's just not relevant. The hyperbolic theory is just not relevant. Now, finally, I mentioned for general models, this is the result of Metivier. If you have sufficiently small amplitude shocks for a classical type of model, genuinely nonlinear, strictly hyperbolic, and symmetrizable, then the shocks are just stable. And that's that's actually very technically difficult to show, but very strong and general results. The questions that we want to address by the viscous theory are, well, we'd like to know the regime of validity of these results. The hyperbolic theory is valid on some length scales. What are the scales where it is valid? What happens in the non-classical cases like MHD? And just what's the meaning of these, in general, what's the meaning of these results, these beautiful mathematical results? Now here are a couple of puzzles. I alluded to one already. Here I've drawn the Hugonio curve as a graph in speed versus pressure coordinates, which are useful for gas dynamics. This is a picture out of Erpenbeck, basically. And so on this, as you move, so the left-hand starting point, this is zero strength, shock strength. As you move along, there is the green zone is strongly stable. Then there's the green zone is neutrally stable. Then there's a transition point. It's actually one-dimensional instability. And you transition to strong instability, and then you can come back to be weakly stable again and then strongly stable. So this is obviously not an ideal gas law here. There's a loss of monoticity in the pressure curve, in the pressure relation. But this is what can happen. Now, two puzzles here are, a funny thing is that One-dimensional instability is intermittent. It just occurs at points. It's codimension 1. So how can it be that as you increase the shock strength so far that the shock becomes unstable, then it immediately comes back to be one-dimensionally stable? That doesn't seem very physically reasonable, and it's not. That's an artifact of the hyperbolic theory. And the other point is that we have this zone of neutral stability. It's an open interval, and we don't know exactly where the transition to instability happens. And Maida suggested that that was determined by nonlinear effects, and of course it could also be viscous effects. Actually, I think it depends on the particular setting that you're in. But we'll show in certain settings it's the viscous effects alone. I point out scalar shocks are always weakly stable. So this is not necessarily, it's not necessarily instability. It certainly could be stability. That is weakly stable in the viscous sense as shown by Goodman. And yet they're always neutrally stable, as pointed out by Maida, in the hyperbolic setting. Okay, now let's go to viscous stability very quickly. We'll just write down, again, we write down some linearized equations. AJs are the Jacobians of the flux matrices. Those appeared before. And now we have some parabolic term. We can do the same normal mode analysis, and that leads us to a generalized eigenvalue equation as before. I won't write it out again, but it's an ODE in X1 again. That's all the same. The difference is we have variable coefficients now. The coefficients vary in X1. They are asymptotically constant at infinity, but not constant. But nonetheless, using some asymptotic ODE results, we can pursue a similar construction. We can carry out some calculations using the fact that solutions to an asymptotically constant ODE should approach to solutions of the constant coefficient limit. We get another determinant condition. But the difference here is we cannot explicitly evaluate it. We can't hope to. But we can nonetheless get some results. So now here the columns are just some solutions of the generalized eigenvalue ODE. And it turns out there's a split. N of them decay at plus infinity, n of them decay at minus infinity. We're looking for decaying solutions, eigenfunctions, so that means that there must be a dependency. There must be some dependency between the solutions decaying at plus infinity and minus infinity. That identifies existence of eigenfunctions, and this is called the Evans function. And stability clearly, again, requires that this function not vanish for the real part of lambda positive. That would mean a growing mode. Now here's the fundamental theorem. This is really the starting point of the mathematical theory, and this was obtained with Denis Serre just in 1999. D, the viscous stability function, Evans function, and delta, the hyperbolic stability function, are tangent at the origin. So in particular, we can express D as gamma times delta plus some higher order terms. That's second order and higher, where gamma is constant, and it's just a transversality coefficient for the connection problem for the shock profile, the ODE problem for the shock profile. Okay, now the proof is actually very simple. The idea is, and actually the motivation for the result, a posteriori, it's simple because we're looking at the low frequency limit. Now the low frequency limit of behavior of this equation, only the lower order derivatives are important. Quadratic terms, second order derivatives are important for high frequency, not low. So that means the behavior should be basically hyperbolic, first order homogeneous. And that motivates our proof. Since it's first order homogeneous, that means, and yet we don't expect it to be analytic, but it's homogeneous, we should go along rays through the origin. That's what we do. We Taylor expand along rays through the origin, and we do some matrix operations based on conservation to reduce to a block form. And I won't go into details, but I'll mention we explicitly separate some hyperbolic type modes from parabolic modes in this matrix manipulation, and that's one observation. The other is regularity plays a very important role here that's hidden in my discussion, and that is when I write higher order terms, that means that I'm using Taylor's theorem, and that means I'm assuming some differentiability in xi, tilde, and lambda, or rather along the ray. And that's not obvious for the reason that we're moving through the origin, and the origin is a distinguished point. It's the point where the essential spectrum of my operator meets the resolvent set. It's just on the border, so that's a singular place, and what was needed to get the regularity is a new idea called the gap lemma, and I'll talk more about that below. But that was a non-trivial aspect that was developed with Gardner, the gap lemma, in the 1D setting. So an immediate consequence, this is again with Serre, is that both transversality, that gamma should not be 0, and the hyperbolic stability, that delta should not be 0 for real part of lambda greater than 0, are necessary. They're necessary conditions for viscous stability. And here's a picture of the proof. The fact that the tangency between delta and D implies, under appropriate non-degeneracy condition, that their zero sets must be tangent at the origin. So we have the conical hyperbolic spectrum in blue, and we have tangent to that, the black parabolic spectrum. Well, here I've drawn an unstable hyperbolic spectrum, and we see there must be nearby unstable parabolic spectrum. And so therefore, hyperbolic stability is necessary for parabolic. It's not sufficient, however, because you see here I've shown for high frequencies, you don't know what could happen. It could start out unstable and go back stable, and the reverse could be true as well. So you could have purely stable hyperbolic spectrum, but the parabolic spectrum could curve back for high frequencies and have strong instabilities. So that is not addressed. So that really tells what the hyperbolic theory is telling us. First of all, it rigorously justifies the hyperbolic theory as being necessary for stability. And well, it also explains what's going on. There's hidden in the parabolic theory, there's hidden in the long time stability problem a singular perturbation. The singular perturbation is as frequency goes to 0. It's not a vanishing viscosity singular perturbation, but it's related. And that's why we got the separation into hyperbolic and parabolic modes. Okay, I'll skip a few of these. I'll just mention that this is very general. It applies to incomplete, complete parabolicity, incomplete parabolicity, and we could even view the hyperbolic condition delta as a version of this. Moreover, in the overcompressive case, from this limit, we can define a hyperbolic-like stability function, delta, that doesn't come from a hyperbolic problem, but gives a long wave or low frequency stability condition. So it gives you a formula that's more robust than the hyperbolic ideas for generating from complicated higher order derivative parabolic models some kind of algebraic condition that gives necessary conditions for stability. Useful engineering type information. The one-dimensional hyperbolic instability. I mentioned that this was intermittent, and that's puzzling. Well, it corresponds to crossing of an eigenvalue, it turns out, from the parabolic point of view. And you can pursue this, and you can actually get a stability condition. That is, there's a sign condition. It's not that only that delta should be non-zero, but it should have a sign in the parabolic setting. This gives you an open condition for one-dimensional stability, which is correct. Finally, in the case of, this is the most important one, in case of the neutral stability, the case Maida's weak stability, in which stability is not determined, the viscous stability condition can actually determine the transition to instability. And you have to refine it a bit. What you look at is, we have tangency between parabolic and hyperbolic spectra. You look at the second derivative. You look at whether it's convex to the left or concave to the right. And that tells you whether it actually crosses. Remember, they're both tangent to the imaginary axis. You just need to go to the next order, which is given by viscosity. And so that allows you to fix, in principle, to fix the transition to instability. Now, that hasn't been evaluated yet, but we hope to. Okay, let's now state this in a different way. What we get out of all this are what I like to call a mixed parabolic and hyperbolic stability condition. We first have the original stability condition, that the Evans function d should not vanish for positive real part eigenvalues. That just means we have no exponentially unstable modes. And also, gamma times delta should not vanish. So that's transversality plus hyperbolic stability. And if you think about behind all this, there's a matched asymptotic expansion going on. And if you think about that, these are just the conditions, natural conditions for the matched asymptotic expansion to be valid. Transversality says that the inner shock structure problem is well posed, and hyperbolic stability says the outer solution is stable. Okay, those are necessary conditions that we've discussed so far. Those are of the main physical interest, I believe. But now let's go on to the mathematical foundation problems. If we strengthen these, so analogous to what MITA did, let's now impose strong stability. We'll say that the Evans function should not vanish even for real part 0 as well, everywhere except for the origin. And likewise, that the hyperbolic type stability should be strong. That's MITA's strong stability condition. Well, then it turns out this is sufficient for linearized and nonlinear stability also in the viscous setting. And in this case, we're going in the reverse direction. I would say up to now, we've used the parabolic theory to shed some light on the meaning of the hyperbolic theory. Here, we're really going to use the strong linear estimates that were obtained in the hyperbolic theory to get corresponding estimates for the parabolic theory. So there's a nice exchange of ideas between the two theories. Okay, so this is a theorem proved that appears in some in summer school notes from Kokolam Z summer school in 2001. Now let me just, I'm short on time, so I'll just state in words what it says. It says if I take a perturbation U of an initial planar shock wave U bar that's sufficiently close in LP and is Holder continuous, then U decays to U bar in all LP P greater than or equal to 2 at the rate of a heat kernel. But it's not a full dimensional heat kernel, it's a D minus 1 dimensional heat kernel. And okay, so just to give a brief idea of the proof. Now we're talking about stability, positive stability results. We need to replace the eigenvalue equation, which we had above, by a resolvent kernel equation. It looks almost the same. Instead of looking for eigenvalue solutions, that is looking for a 0 right-hand side, we put in a delta function forcing at y1, and we look for the kernel, which satisfies eigenvalue equation. Eigenvalue operator applied to it is the delta function. It turns out this kernel, G of C tilde lambda, that's the Fourier Laplace transform of the time evolutionary Green's function G. That's the thing we want estimates on. And the nice thing is, again, this is an ODE. And there are solution formulae for the Green's function. They're semi-explicit in the sense that you can write them down, but they're not, and you can get estimates. But they're not, of course, it's not constant coefficients, so you can't write down what everything is. But here's what it looks like. It's a sum of coefficients, which depend only on the frequencies, times solutions of the eigenvalue equation, which decay at the appropriate infinities. And these depend both on the frequency, but also on x1 and y1. And M, it turns out, is approximately the inverse of the Evans matrix. So it can be measured by the inverse of the Evans function. So that gives, and actually it turns out it's a pole of order 1. And that gives you an idea of what's going on here. That's why we lost one dimension. That pole basically kills one dimension. And the pole arises from translational invariance of the background wave, which tells you that there is a 0 eigenfunction, always. Okay, and this corresponds with a fundamental paper of Jonathan Goodman in the scalar case, where he observed basically the time asymptotic behavior is given by translation, deformation of the front, and that evolves, one could think of that evolving as a diffusion equation along the front. So that's one dimension less, and that's what we have in mind there. Okay, so now I'll just point out, how do we get these estimates? Well, we estimate the inverse of the Evans function by this fundamental theorem that relates D to delta. So we use hyperbolic estimates there. And the W's, which were the solutions of the eigenvalue equations, those are estimated by asymptotic ODE results, comparing them to constant coefficient solutions. And that gives us very sharp bounds in both the frequency and spatial variables, and through the Laplace Fourier inversion formula, then we can convert those rather easily, actually, to sharp parabolic bounds on the time evolutionary Green's function. And that, in turn, extremely easily yields nonlinear stability, which is a bit surprising that it's also so easy. The hard part, because in 1D, that's not at all, those steps are not at all easy. But the hard part here, which does not appear in 1D, is the estimation. Really, I glossed over the difficulties here, the estimation of those resolvent kernel estimates. And where's the difficulty? It's the same one, but the difficulties really are inherited from the hyperbolic theory. The difficulty is so-called glancing modes. These are branch singularities in the matrix perturbation problem of the coefficient matrix and how its eigenvalues and eigenvectors perturb as frequency increases. There's a new issue that does not appear in the hyperbolic theory, and that is blow-up of our coefficients when we look for bounds between LP and LQ with P different from Q. Now, in the hyperbolic theory, it's always L2 to L2, and you don't see this blow-up. It's a blow-up in frequency only, and it turns out it's integrable. It's sort of a coordinate singularity. In going from Laplace, if you take Fourier transforms, you don't see it. It comes from the incompatibility between Fourier and Laplace transforms, basically. But it's really a coordinate singularity. It's harmless. It integrates. It's just an integrable factor in the Laplace-Fourier inversion. So that turned out, from the technical level, once understood, it's not difficult. What I mentioned, it's really there, and you can see it also even in solution theory for the wave equation, where you find bounds from, say, L2 to L infinity. They are singular. You don't have uniform bounds. And, okay, again, transition to instability is now determined by the viscous correction, and we also have that in terms of the positive stability results. Okay, finally, just briefly, the issue, some of the results I mentioned, in particular the last one, are for strictly parabolic viscosities. But it doesn't appear, at the moment, it doesn't appear that that is a real issue other than a technical one. That is, there's no new behavior. And in 1D, this problem is resolved, and it seems to be very close in multi-D. So that's, I think that's not one of the main issues. Okay, now I mentioned also, in the hyperbolic setting, once the planar condition delta, which was algebraic, was obtained, one could directly work with it and obtain very strong results. That is, the explicit results for gas dynamics and Mettivier's result for small amplitude shocks. So what do we have for the viscous case? Well, the viscous case, it's really an ODE problem because we have variable coefficients. We don't have an it's not really an algebraic condition, but an ODE one. However, one can mimic the Mettivier theory, it turns out, and show that at least small amplitude shocks of classical type systems are stable. And this has recently been obtained, actually doubly obtained, by Ramon Plaza and myself, and also by Heinrich Freistruller and Peter Simoian, from rather different points of view, I should add. And alternatively, we could verify numerically. This can be numerically checked in a well-conditioned way, and this was Len Brin, a student of mine, has carried out, for example, one version of this in 1998. So that's quite reasonable. But I think a key open problem for the theory would be the analytical evaluation of the stability condition, this ODE problem for strong shocks for important models like gas dynamics. Okay, so that's where the planar theory sits. And I think it's fair to say we've essentially answered all the questions in the planar setting, with the exception of the strong shock problem. And so that's something like, we're up to about the Erpenbeck and Agman theories. That is, in terms of the necessary conditions, we've really identified them, we've answered the physical questions, and we've done some explicit estimates. That is, for the constant in the planar setting, by explicit inversion of Laplace-Fourier transforms and explicit estimates, we've shown nonlinear stability, linearized and nonlinear stability. This is sort of analogous to what was done by Agman in the boundary layer case, in the boundary value problem case setting. And now we want to turn to the curved shock or boundary setting. And this is like the Kreis and Maida theories. So Kreis, basically, his big advance, one of it in this area, was to show how to replace these explicit estimates by more robust energy estimates, and that were really convenient to use, convenient for the pseudo-differential setting needed for the nonlinear and curved problems. Okay, so the first problem here, though, is what is the problem we want to solve? What do we mean by a curved viscous front? Just as in the hyperbolic setting, we don't have them lying around. We don't have explicit explicit curved solutions, not as in the planar setting. And here's our answer. This is not necessarily the most interesting one, actually, but this is the more approachable one and the more exact analogy to the Maida theory. So we just say if we can find a family of solutions u epsilon, which are converging to a curved hyperbolic front in the vanishing viscosity limit of the same parabolic equations, but now with an epsilon in front of the parabolic term, and we're letting epsilon go to 0. And the main theorem that we have here, this is very recent, just this year. This is with Olivier Guess and Guy Metivier, Mark Williams, and myself. And this is in the strictly parabolic case. So suppose we have a curved hyperbolic front solution u naught, and it exists on a bounded interval of time and sufficiently smooth, as given in MITA. Moreover, it must satisfy these two conditions. Script D1, these are analogous to D1 and D2 previously, though I reversed the order. For each point belonging to the shock surface, this is the hyperbolic shock surface, there must be a viscous connection, a planar viscous connection. Lax type in this basic result for the corresponding planar ideal shock. Moreover, it must be strongly stable in the sense of Kreis and MITA. That is, the ideal shock must be. So transversality and hyperbolic stability. That was the old D2. Okay, here I have to state it first so that D2 is defined. Moreover, for each point on the shock surface, the associated viscous profile is spectrally stable. So it satisfies the Evans function condition. It doesn't have strongly growing modes. In other words, our strong planar stability condition holds for each frozen planar system as you look tangent to each point of the shock surface. Moreover, technical condition, we assume that the hyperbolic front is nearly flat. It has sufficiently small variation. Then there exists a family of solutions u epsilon of the vanishing viscosity problem, above 7 here, which converges to in L2 at rate order of epsilon to the original hyperbolic solution. So that's a very, very satisfying solution other than the flatness condition. However, the flatness condition can't be removed. But I mentioned this is what might be called a prepared data result. That is, we allow ourselves to design in the initial data that leads to a nice solution close to the hyperbolic one. So this is analogous to the work of Goodman and Shin in the 90s. Shushen Yu in 2000, I believe, did the 1D problem for unprepared data. This is much, much more difficult because the biggest error in the solution is the initial layer from going from a discontinuity to a viscous solution. Okay, so that's a problem for the future, very hard. The nearly flat assumption can be removed. And okay, so I'll just mention briefly a couple of the ideas. So basically, we're going to approach this by ideas from the long time stability problem, because a bounded time vanishing viscosity and long time asymptotic stability, these are related by scaling, basically. As you look, because as you keep the Reynolds number fixed, you need to scale xt to x over epsilon, t over epsilon. So that bounded time goes to infinity. But they're not exactly the same. And one difference is, in the small viscosity, or SV problem, you have an initial step that wasn't there at all for the long time stability problem. You need to construct an asymptotic, matched asymptotic expansion to begin. And this is a non-trivial step. Then the idea is you're going to show that expansion truncated somewhere is stable. Is linearly stable, and you'll use that fact then to convert the formal error into a convergence error and by some iteration. That's almost always the way it's done, but there's not a really clear separation between these two steps. That is, if you get a very good accurate series, then you need only weak stability estimates, and vice versa. Okay, so I mentioned that this first step was carried out already by Olivier Guess and Mark Williams in 2001. To arbitrary order. That's remarkable. That wasn't done even in 1D. And they have a very nice point of view, which is non-standard. They viewed it as a free boundary problem at a shock surface, which they prescribe, with transmission conditions, which are artificial. They just match the zeroth and first derivatives. So they viewed it, they want to view things, they come from the hyperbolic point of view, and they wanted to view things more in that way. That turned out to be profitable because they found out that they only needed those two, basically the hyperbolic information, to construct this series. Okay, now the second difference is, in the vanishing or small viscosity problem, we basically need only L2, we can use only L2 to L2 estimates, essentially, because in the problem there is the hyperbolic solution sitting there. And as pointed out by Jeff Rausch and others, basically L2 is the only good norm there. You have bad behavior when you go between either LP and LQ. And we need to obtain these in a way that is uniform between the outer, basically hyperbolic, and the inner, parabolic, shock layer problem. So a first step was an analysis of a simpler problem, which was the boundary layer version of this problem. That was done by Guy Metivier and myself in just this year. And our idea was to use Kreis symmetrizer analysis. Now, the Kreis symmetrizers were the technique used by Kreis and then Maida to analyze the hyperbolic problem. And it's basically, you find a nice pre-multiplier, a symmetrizer, which then gives good energy estimates both in the interior and in the boundary terms that arise. So you get trace information and L2 interior estimates. And these, basically the whole pseudo-differential machinery that exists in the hyperbolic theory, it's all designed to, it integrates with this method. So that's very promising if you can do it. And it turns out there are two key ideas. Okay, the first one is an improvement of the old gap lemma. Now, I briefly mentioned the gap lemma, but I didn't state it. So now here I'll state it. Here's the gap lemma, the ODE result behind which we got all our estimates for the planar case. Let's just look at a first order ODE. W prime is A of gamma x W. So the coefficient depends on x, which is the spatial variable, and also some parameter, which you should think of as frequency, because this is like a generalized eigenvalue problem. A is analytic in the frequency gamma and smooth in x, and it converges exponentially in x to limits at plus and minus infinity at a uniform exponential rate. That's what we get from these traveling wave problems, because our profiles, the background profiles, are exponentially approaching to their limits. Then the basic gap lemma, the one proved with Rob Gardner, and then changed. This version I state here was a modification proved with Peter Howard in the 1D setting. Suppose this coefficient matrix, the limiting coefficient matrix A plus, has an analytic eigenvalue eigenvector pair, mu plus and v plus. These depend only on gamma, of course. Then, under that assumption alone, there is a solution of the variable coefficient problem, which looks like the solution of the constant coefficient problem. That is, it's e to the mu plus x times v of gamma x. Okay, so instead of v plus of gamma, we have v of gamma. But this is still analytic in gamma, and it satisfies this strong estimate that the variable v minus the v plus is exponentially decaying at roughly the same rate as the coefficients. And you can do symmetric, but these are estimates that are good for x positive, of course. We can't go past. That would be using information we don't have. And the proof is extremely straightforward. It's a standard fixed point iteration from any ODE, any asymptotic ODE book. So the only point here is just to make the statement, to observe that this is true, and then you can immediately prove it. And the main point is we did not make any requirements on the spectral projections associated with these. That's really the crucial point. And therefore, or also, what's the gap in the title? It refers to spectral separation of different eigenvalues, which in the standard theory is required, and that has to do with these projections. Here, basically, that doesn't come up because the exponential decay kills any problems due to branch points. And the region of analyticity that you get is determined by the allowable spectral overlap, which is given to you by the rate of exponential decay. Basically, the goodness of the exponential, the fast decay to constant states gets rid of algebraic growth due to branching. Okay, but now here's the improvement. Now let's consider a forced version of this system. So that was sort of an eigenvalue problem. This is a resolvent equation. I just put in a forcing with the same problem. And here's the lemma with Metivier, the conjugation lemma. It says there's a smooth, uniformly well-conditioned coordinate change, P. So set W equal to PZ, such that this resolvent equation is conjugated to a constant coefficient version. And the coefficient is that the limiting is the limit of this coefficient at plus infinity. And this, again, is only on x greater than or equal to 0. And the coordinate change satisfies the following estimate. It's asymptotic. It's exponentially converging to the identity at plus infinity. So this, now the proof is immediate. You just write the equation. You put this ansatz in, write down the equation that you get for P. Here's the matrix equation. It's a commutator type equation. as always occurs when you do this sort of thing. And notice, the limit at infinity is a plus p minus pa plus. That's the limiting coefficient system at infinity. That has a trivial solution given by the identity. So if we view this as a vector equation, then this is a linear transformation which has in its kernel the identity. The limiting version, constant coefficient version, has the identity in its kernel. So we have an eigenvalue eigenvector pair given by mu identically equal to 0, p plus identically equals to the identity. Trivially analytic. We apply the previous theorem, and we immediately get this result. So it's at a technical level, it's a trivial extension, but it's much easier to use because it gives you direct control of the equations, whereas before we had to work very hard. What this does is it reduces our problem to a constant coefficient one, with now the boundary conditions change. Looking at it from the point of view of Guess and Williams, viewing everything as something with, we have these artificial transmission or boundary conditions. Now, but we knew what they were. They were trivial, just matching of derivatives and values. Now it's something that we don't know because there's this coordinate change intervening. So we call these twisted boundary conditions. We don't know what they are anymore. Now it's really like the Kreis or Maida problem. And now we can apply Kreis-symmetrizer techniques. And the first observation goes back to the result with Serre that we can decompose into hyperbolic and parabolic blocks. And the parabolic blocks are trivial to deal with, to find a symmetrizer for it. The hyperbolic blocks, basically the symmetrizer for those is the same one found by Kreis. A little bit more complicated because there are some extra parameters, but same idea. And then you make the observation that the nice thing about the Kreis approach is the estimates you get are really, the symmetrizer is independent of the boundary conditions. And you just need boundary conditions that are good. What does good mean? It means the hyperbolic stability condition holds. So again, everything closes up neatly, and the hyperbolic theory really drives the parabolic estimates. Okay, there's one, just want to mention, for the shock problem, there's a new issue. It's the same difference between Kreis boundary value problem theory and Maida's theory in the shockwave case. The boundary conditions are degenerate. That's again because of translational invariance and the fact that there's an eigenvalue for the problem at zero frequency. From our point of view, that means that there's, that the boundary conditions are not transverse because they don't disallow this eigenvalue problem. So the Kreis estimates cannot be true because they're equivalent to having a transverse boundary condition. So a first approach was to modify the Kreis symmetrizer approach. We introduced these degenerate symmetrizers, which recover the good interior estimates of Kreis, but we give up something on the trace. And that's exactly what should be true, basically, because and we give up the trace estimates only in one direction, which is the direction of degeneracy, which is the direction in which the shock front deforms. It's the direction of the zero eigenfunction. And that turns out to work. It's consistent with the Maida estimates. You can match them up. It's sharp with respect to when you compare them with the explicit planar estimates of the planar theory, but it doesn't fit very well in the pseudo-differential framework. And the reason is we're not really doing local or differential estimates. We're carving up frequency space to do this and doing things in different ways. It didn't fit that well with the pseudo-differential calculus involved in the next step, and that resulted in our flatness assumption, which was just due to technical difficulties. But we have a newer approach that's worth mentioning briefly. And it's closer, actually, to the hyperbolic theory. We introduce a front location as an artificial additional variable. This is also closer to the original Guess-Williams asymptotics. We prescribe an appropriate local that is a differential description of the front evolution. And this restores a good boundary condition, it turns out. And now you can use, really, the Kreis estimates. You recover the same estimates, however, because when you filter the good Kreis estimates through this new variable, you get the estimates from the degenerate symmetrizers. So we don't get any new estimates for the planar case, but the real thing is that now it fits well with the pseudo-differential calculus, and we can throw out the flatness condition. Also, I find this much more illuminating. And I'll just mention to you briefly what is the front evolution that's given, because it's a little bit interesting. It's so simple. You just introduce a new variable, which is a shift. So u tilde is a shift of the original solution u by psi, where psi of x tilde t is your shock location, your new variable. And psi is determined by this condition. Its derivative should be negative L dot u of 0. By the way, this shifts the shock location to 0. So now 0 is the shock location, so the presumed shock location. So this, and L is designed so that its inner product is a constant. Its inner product with the derivative of the traveling wave be 1. So it identifies, what it identifies is some shock structure near the origin. Now there should basically be none. This identifies a translate of the shock. There should be no translate. It should be just centered. If U prime L is not 0, then it says the shock is a little off center. And what you do is you move in the opposite direction. So you just try to push away any shocks that you see. And a really illuminating example is just take the trivial example of a shifted planar shock and see what happens to our shock location. It turns out it just is an exponential decay. It just exponentially decays to the correct solution. And this is really interesting because, well, people have tried for a long time to define the notion of a viscous shock location. I know I certainly have, and Goodman had many ideas. And Goodman's approach was basically do a least squares approximation, sort of try to fit as well as you can to the shock wave. Notice we're not doing that at all here. We're just saying whatever passes by, we'll just kind of try to push it away. And I have tried to do that with Howard by we did the opposite. We used a non-local description in which we looked all the way forward in time and just used our Green's function estimates. And that's really sharp, but it doesn't, it's not, again, non-local, and that's not good for this theory. This is really simple, and it seems to recover all the advantages of the two methods I mentioned. Finally, some open problems. Well, the unprepared data problem that I mentioned, that's quite open, and we've thought about that, but it seems very hard. And here's another problem altogether, a different version of the curved shock problem. We would really like to understand about shocks with finite thickness. To me, that's what a real curved shock is, because the curvature affects the stability in reality. And that's due to the thickness of the layer. We don't see that at all in this vanishing viscosity theory that we've introduced. And I think physically that's the really interesting problem for detonations, for fusion, et cetera. And I don't even have a suggestion to make, but I think that's the direction to go. Okay, thanks for your attention.
Questions, comments, please? Well, I have some questions. There are some curved shocks which have special geometry and therefore have special interest. Like you actually present the analysis for either planar or general, sometimes general.
Right.
So how about spherical shocks, elliptical shocks, and stuff like that?
Well, that I think you could approach. Yeah, that's in terms of a suggestion for number 2, I guess that would be my suggestion to look there. But the one problem is, you see, it's not anymore time invariant. The planar shock is a time invariant solution. And these other ones are slowly time varying, but of course, those are all expansive, right? They're expanding with time. They're not steady. And so that's another technical problem, is how to handle that slow variation. When everything, slow variation is not a difficulty in the ODE type setting or in the setting where you can sort of isolate a slow manifold of what's really happening. But here, the slow manifold is not very well separated. The slow manifold is basically that zero eigenfunction corresponding to translation or deformation of the front. There's no spectral separation between that and the essential spectrum of the operator. And that's the reason that it's not easy to project that off. You'd like to project that off and treat that solve that ODE, and then treat the rest as an error. That's how you generally deal with slowly varying coefficient problems in a semigroup type. This is really a semigroup type viewpoint. But I don't see an easy way to do that because the projections are not so well separated. But I have to think that these kind of problems could be approached.
Okay. Thank you.
So the planar condition is relevant to that, significantly different planar condition?
Yes, that's right. The planar condition, right? That's where it arises. Yeah, that's exactly right. Mm-hmm. It indicates that difficulty. And you see, for the finite thickness problem, for these problems that Dan mentioned, that would necessarily be changed. It would not be the same delta. It would have to be shifted and in it would be the thickness of the shock, the radius, that is the radius versus the viscosity, and it would be very interesting to find what that condition is, and very useful. It's not in this framework, or even Sonic, or even Sonic. That's, you know. For example, in the boundary layer setting that I mentioned, we explicitly take non-characteristic boundary layers. So that eliminates the physically interesting case, the whole Prandtl theory, and you know, what people care about. That was really a warm-up problem for shocks, what we did. It's not a physically interesting boundary. I don't feel it's very physically interesting. But so no, these techniques, that's a harder problem, and these techniques don't address that.